Hello and Namaste. In continuation of the complex integration, we are going ahead with the Cauchy's residue theorem. After the detailed introduction about what exactly the residues are and the different way of finding out the residues at the different poles. Now, what is the statement of Cauchy's residue theorem is, if f of z is analytic inside and on a simple closed curve C except at a finite number of singular points inside C, then we have integration, or you can say the integration f of z dz over the closed curve. So this is the symbol for the closed curve C. So that is not, this is giving us that this particular curve is closed, which is equals to 2 pi I into sum of the residues, where the integral is taken in the anticlockwise direction around C. Now we are accepting the statement of the particular theorem without going ahead with the detailed or you can say a proof behind this particular statement. So we are just going ahead accepting the proof, accepting the statement for the solving of the examples. Now evaluate integration of 3z square plus z minus 1 upon z square minus 1 into z minus 3 over the curve C dz, where C is the circle mod of z equals to 2. Now let this particular function, so this is whatever is the integrand, this is nothing but the entire function f of z, can be written as z minus 1 can be split it into 2, so it's a square minus b square, can be taken it as a plus b into a minus b, z minus 3 as it is. So we have got the poles as minus 1, 1 and these are the 3. So we have got minus 1, 1 and 3. If you'll observe here, C is the circle mod of z equals to 2, which is the center at the 0, 0 and the radius is equals to 2. This particular statement we have written it because we know that z minus a plus ib is equals to small r, and that is what we can say that okay, a comma b is the center of the circle, which is 0, 0 in the present case, and r is the 2 here in this case. Now for z equals to minus 1, that means we have to take a call whether this particular z equals to minus 1 as this particular pole here is the point which is there inside or outside the circle. So this is what we have already seen. We are trying to find out the distance between the center of the circle and that particular point. If you'll observe here, it is coming out to be 1. The distance is 1 unit, which is less than 2. So this lies inside this particular circle C. Similarly, if we could observe that this z equals to 1 will also be lying inside the particular curve C. And if you'll observe, z equals to 3, which is mod of z, which is mod of 3, it's equals to 3, which is greater than 2. Hence, z lies outside the C. So we are not supposed to consider this z equals to 3 to find out the residue for this particular function. So we have to find out the residues at z equals to minus 1 and z equals to 1, but not for z equals to 3 because it is outside. So this particular point lies outside, so we are not supposed to find out the residue at this particular point. So z equals to minus 1 is a simple pole. We are aware of this is the formula. Residue of f of z at z equals to minus 1 is giving us limit of z minus of minus 1, that is z plus 1 here, f of z, which is giving you this type of thing, that is limit of this entire function. Out of that, this z plus 1 and function this f of z, we have this z plus 1 will go off, and that's the reason we do not have this z plus 1 in the next step. So this z plus 1 will go off from the function and this particular point, and we will be getting the value of this as 1 by 8. So this is just a residue of the function f of z at z equals to minus of 1 as 1 by 8. Similarly, z equals to 1 is a simple pole. Again the same way, it is z minus a. A in this case is 1, so it is again going to be cancelled from here, and you will remain here with the function as this z 3z square plus z minus 1 upon this. And if we put the value of every z, if you're replacing with 1, we are going to get the value as minus 3 by 4. And therefore by Cauchy's residue theorem, the statement is this, which is 2 pi I into sum of residues. We have got two residues, 1 by 8 and minus of 3 by 4. So addition of them into 2 by I is the value of the integral, which is nothing but minus 5 pi I by 4. So this is what is the answer for the first question of using the residue theorem. If you will observe the point, we have to find out the residue only at those points which are lying inside the circle or inside the given curve. Otherwise we are not going to find out the residue at that particular point. Like here in the case, we did not go the residue at the point 3 as this is outside C. So we did not find out the residue of the function f of z at z equals to 3. We did not find out that. Okay, and this is the answer, minus 5 pi I by 4. Evaluate the residue theorem. Using the residue theorem, evaluate integration e to the power z plus z upon z cube minus z dz over the curve mod of z equals to pi by 2. Again, the same way, z cube minus z can be splitted as z into z plus 1 into z minus 1. Again, we have got minus 0, minus 1 and 1. These are the three residues. Now, whenever we are talking about distance, as I have already given you in the previous sessions also, that pi is pi is having two different values. One is 3.14, another value is the 180 degrees. But now here in this case, we have to compare with the distance. If we are comparing with the distance, we have to take the value of pi as 3.14 and not 180 degrees, because we have to think about the distance. So we are taking it, mod of z is equals to pi by 2 is 1.57, that is 3.14 by 2, with the center 0, 0 and radius as pi by 2. Again, we have to take a call whether the 0, minus 1 and 1, they are in or out of this particular circle. So if you observe this 0, obviously 0 is less than pi by 2. Similarly, this 1 is less than pi by 2. Please observe the steps, what we have done, the steps. We have already done this similar type of steps in the session where we have talked about the Cauchy's integral theorem. Please follow the I button to reach to that particular section or a session. And again, if you observe this for z equals to 1 also, again this is less than pi by 2, that is less than 1.57. That means what, all these 3.0, minus 1 and 1, all of them are lying inside. Again, if you observe, all of these 3 points are inside the circle, and all of them are simple poles. So z equals to 0 is a simple pole. The same formula what we have done it, z into f of z, it will gives us like this. So we can easily find out. I'll just go ahead little fast forward way, because it's just a simple pole we have discussed on, and we have discussed in a very detailed manner how to find out the residue at a simple pole and how to find out the residue at a multiple pole. So my target is to make you realize or make you familiar with the Cauchy's residue theorem, that is after going ahead with the addition of the residues and multiplying that with 2 pi I. So z equals to minus 1 is a simple pole. Again, this is the same way what we have done it. Pause the video, try to get the answer as what I am getting on the screen. Again, z equals to 1 is a simple pole. The same way, I'll just, as I've told you, I will little fast forward here. So e plus 1 by 2 is the residue of the function f of z at z equals to 1 using the simple pole formula. Now, using this residue theorem, it's 2 pi I into the sum. So it's minus 1 for the first, 1 minus e upon 2e is the second, and third one is e plus 1 by 2 is for the third one. So if you'll add them up, and if you'll just adjust taking the LCM and adjust the terms, you are going to get the answer as pi I by e into e minus 1 the whole square. You can keep this e square minus 2e plus 1 as it is. Otherwise, you can go ahead with this also as one of the format for this particular answer. So z, integration of z sec z upon 1 minus z square dz, where c is the circle mod of z equals to 2. So I have considered the problems in this particular session, wherein every problem will have the different approach to deal with. So this is, again, if you'll observe here, this is sec z in the numerator, but as we have to go ahead and find out the singular points of this particular function, we have to find out the singular points at all these points. So that means sec z we have to write down as cos of 1 by cos of z, and therefore it is nothing but, again, this 1 minus z square we can take it at 1 plus z, 1 minus z into cos of z. Now we are going to go ahead with, again, the same thing, mod of z equals to 2, which is the center at 0, 0, radius as 2. Poles are given to us, this, the product of them is equals to 0. That means what, 1 minus z square is 0 and cos of z is 0. That means z equals to plus or minus 1. So this plus or minus 1 you are going to get it from the first bracket, and second is cos of z is equals to 0 means z equals to plus or minus pi by 2, plus or minus 3 pi by 2, and so on. Out of that, which points are lying inside this circle is very important. Now let us consider here z equals to plus 1 or a minus 1. If you will observe here, both of them the mod will come out to be 1, and that means what, in both the cases z equals to plus 1 is inside, z equals to minus 1 will also lie inside this particular C. What about the other point, z equals plus or minus pi by 2? If you'll observe here, plus or minus pi by 2 is 1.57. The mod of that will gives us 1.57, again which lies is inside. But if you'll observe here, plus or minus 3 pi by 2 will gives us the value as 4.71. So it's minus 4.71 plus 4.71, mod of them will gives us 4.71, which is going to be greater than 2. That means this particular point lies outside the C. If it is lies outside, we are not supposed to find out the residue to get the value of this evaluation part. So we are not supposed to find out the residue at this particular point of plus or minus 3 pi by 2. Again, the next point, if you'll observe here, the next point will be plus or minus 5 pi by 2. And if you'll observe again here, if this 3 pi by 2 is going to be out, obviously the all other rest of the points will be going outside this particular circle C, or mod z equals to 2, and hence we are not even considering them. So we have to just find out one, and if it is not there, then rest of the other points won't be inside this particular circle. Now, so only poles z equals to plus or minus 1 and plus or minus pi by 2 lies inside C. So 1, 2, 3, 4 residues we need to find out in this case. So I'll just go quickly because all of them are simple poles. If all of them are simple poles, we have to just go quickly with this z equals to 1, z equals to 1, minus 1. It is minus 1 upon 2 times cos of 1. It is minus 1 upon 2 times cos of 1. So we got the residues at both the points are equal, if you'll observe here. Similarly, for pi by 2, it's a simple pole, and this is what we are going to get it. Now, there is little bit of change. What we have already observed, this type of change in the previous, where we have solved it by the residue or find out the residues using this. Now, if you'll observe here, if you're putting z equals to pi by 2 in the numerator and the denominator here in this case, we are going to get it 0 by 0 form. That 0 by 0 form will exist here in this case. Here exist will in this case, not in the particular first case. So here we will not be getting the value as 0 for z equals to pi by 2, but yes, we are going to get it in the second part, and that's the reason we have to go and apply here the L'Hospital's rule. Now, what is this L'Hospital rule? Says that we have to differentiate the numerator and the denominator differently. That means the numerator, differentiation of numerator in the numerator itself, and the differentiation of the denominator into the denominator. In short, we are not supposed to go for u by v rule. We are not supposed to find out a differentiation by u by v rule. We are not using this. We are using the differentiation of numerator alag se and the denominator differently. So here the first bracket there is no issue, so directly we have put the values of z as pi by 2 in both the cases, numerator as well as the denominator. Second case is little different. As I have told you, the differentiation of z minus pi by 2 with respect to z will gives us 1, and differentiation of cos of z in the denominator will gives us minus of sine of z. And suppose we are putting this z equals to pi by 2 in this case here, now we are not going to get the value as 0, and that's the reason we can just go ahead and now substitute the value of this z equals to pi by 2 here. We'll get the value as this, so minus 2 pi upon 4 minus pi square, which we can rewrite, absorb the minus sign inside, that will gives us 2 pi upon pi square minus 4 as the residue of the function at z equals to pi by 2. Another point is z equals to minus pi by 2 is a simple pole. The same way what we have done it so far, we have to do the same thing again in this case, and we will be getting the value as 2 pi upon pi square minus 4. Again, my suggestion for you all is just pause the video after this, try to get all the steps whatever I've got it on the screen, and then try to cross check whether you are going to get the same answer as that of me or not. Okay, and therefore by Cauchy's residue theorem we are just adding all of them. If you are adding them all together, we are going to get it something like this, and we have got the last answer or the final answer as minus 2 pi I upon cos of 1 plus 8 pi square I upon pi square minus 4, just by adding them up. That is the sum of residues of all these poles which are lying inside the circle. And hence, yes, this is the self-observation slide, which is a favorite of mine. 1, 2, 3 questions have been given to you along with the answers over here. If you are getting any doubt, any difficulty in solving this particular questions, please write me in the comment section so that I can have the discussion in the comments if possible. If it is not possible to have a communication or discussion on the comment section, I will definitely try to give you the solution part of this particular questions. I hope you have understood everything about the residues, the poles, singularities and residue theorem, Cauchy's residue theorem in detail. Thank you so much. Happy learning.